And yes, as Nicole mentioned, I'm going to talk about random order streaming lower bounds for connected components. And this is joint work with my advisor, Sever Asadi. The picture isn't really necessary. He's been around. Yeah, okay, so let's start. Let me define the streaming model first. Okay. Here, we have a graph with n vertices and m edges. And what we know here is the vertex set already. We don't know the edge set. Okay. And how is this edge set given to us? The edges are going to appear one by one. So first edge E1 appears, then edge E2, then edge E3, and so on till all the way till edge EM. Okay. And the issue is we don't actually have a lot of space to store all of these edges. We only have polylog n space. And we want to process this graph in this limited space. So this is the model we're going to start out with. Okay. And so in this model, even for very, very simple problems like connectivity and bipartiteness, even if you want to check if a graph is connected or if it's bipartite, you're going to need omega of n space. And this was proved all the way in 2005 by Feigenbaum, Cunnan, McGregor, Suri, and Zhang. Okay. And these are not the only problems. Even for a lot of other problems, you know very strong lower bounds here. So algorithmically, this is very hard. So processing a graph in this polylog space is hard. So the next step for us is going to be to relax the model a little bit. That's what I'm going to talk about now. So here, I'm going to define a random order stream. Again, you have this graph. The vertices are already known to you. Right? And now, instead of the edges appearing in some order, whatever order it is, I'm going to ensure that these edges are picked in a random order from E. What does that mean? Before these edges are sent, you're going to pick a permutation of the edges. And these edges are going to appear in this order that you picked. And this permutation is completely random. And we'll see how we're going to make use of this and what happens in this model and so on. Okay? So yes, so edge EI1 appears, I2, and so on till IM, where this order I1, I2 till IM is completely random. Okay. And the specific problem that we're interested in is to find the number of connected components of a graph in this model. So any questions till now with the model? Yes?
So you know the set of edges. You know the set of edges and you don't know the order.
No, that's not it. You don't know the edge set at all. It's going to come one by one. Yes. And like we said before, you don't have space to store all of these edges. Okay, you can do whatever you want with the limited space you have, right? But you don't know all the edges. And you definitely can't store all of them because you don't have order of m space.
What's the difference between the streaming model and the random order streaming model?
Got it. In the previous model, in the streaming model, this order that we spoke about, right? Someone who's adversarial to you can just say, okay, fine, I'm going to pick this horrible order for which things are very, very hard for you. Okay, they can do that. But here, in this random order model, you're going to pick a random permutation, and that's the order edges come in. So this is algorithmically easier for you. And why we're doing this is because in the earlier model, things are very hard, and you only have strong lower bounds for it. Okay? Yes. All right. So we want to find the number of connected components here. Okay? So even in this random order model, finding if a graph is connected is going to require omega of n space. And this was proved by Chakrabarti, Cormode, and McGregor in 2008. What we are going to look at is to try and find the number of connected components up to some epsilon and additive factor. Okay? So we're interested in additive approximation of this number in random order streams. Okay? All right. So let's look at some upper bounds for this case. So in 2018, Peng and Solar gave the first algorithm for this problem. And it used 1 by epsilon raised to order of 1 by epsilon cube space times some log factors. Okay. And they were able to solve this. And this upper bound was improved to 1 by epsilon raised to order of 1 by epsilon by Chiplunker, Kelleher, Kapralow, and Price in 2022. Okay. And this same paper also gives some evidence for a lower bound in the space required by this problem. So before that, what I want you to note is that we have this dependence on epsilon on this space, which is actually factorial. You know, it's not even exponential, it's beyond that, it's factorial. Right? And this lower bound is what we're trying to address today. And this paper actually gave some evidence that this factorial lower bound, or this dependence on epsilon, may actually be inherent for these problems. Okay. Next, I'm going to talk about what this evidence is. All right. So this paper defines something which is close to a random order stream, but not exactly random. Okay. So what they did is, before these edges are sent to you, some adversary is going to come and group them into groups of size 2. Okay. And these groups are then sent to you in a random order. Right. So in this model, this paper, CKKP paper, proves the lower bound of 1 by epsilon raised to omega of 1 by epsilon for finding a connected component. Right. So it's not for estimation, it's not for a truly random order stream, it's only for finding a component in this batched random order stream. That's what they call it. Okay. And yes, it's not applied to estimation. Okay. So it still suggests that it may be possible that this actual dependence on epsilon, exponential dependence, may be inherent here and you can't avoid it. Right. So this is what we're addressing. Now I'm going to talk about our results. So we proved that there is no algorithm which actually estimates this number in 2 raised to little o of 1 by epsilon space for this particular value of epsilon, which is in the range of 1 over log n. Okay. So this is saying that this actual dependence on epsilon has to be exponential. Right. Right. And the main tool we used for this, before that, so any questions still about the model? And yes?
So these lower bounds are saying nothing about the dependence on n, they're only saying about the dependence on epsilon.
We do get some log factors in this lower bound too. I just did not put it here because that's not what we're focusing on. Anything else? Okay, so let's keep going. The main tool we use here is something called gap cycle counting. Sorry, did you have a?
I may be confused if we go back about how to parse. So,
Sure.
like, what would be a good like a particular space I should be thinking about, like for some particular epsilon, say it's exactly 1 over log n?
Yes, you can just think of epsilon to be exactly 1 over log n.
And then what kind of space are you getting?
This will be omega of n. Right? Yeah.
We only restrict it cannot be too large, right? But smaller thing it can work. It's just like you are picking the best.
Sorry?
Okay. No, it's just like this works like for a quantity. Like you're picking the best. Like yeah.
Not exactly, no. When we're talking about it, we're actually going to pick this to be exactly this log n, and we're going to use it there.
Yeah.
It's not going to vary for the range. No, this is exactly what we're working with. Anything else? Yes?
Did you already have something like this for adversarial?
Yes. For adversarial, even stronger bounds exist. You're going to have n raised to 1 minus r of epsilon. Right? So it's exponential in n with dependence on epsilon, and that is actually tight. And this was proved in 2016 by Huang and Peng. Anything else? Okay, fine. So after this, I'm going to talk about what we used to prove this result. The main problem here, the main tool we used, was something called gap cycle counting. And as the name suggests, you have 2 different graphs. Okay? So one graph is just a union of cycles of length 2k, right? And you're going to have n over 2k of them. And the other graph, it's a union of cycles of length k, and you're going to have n over k of them. And your objective is to identify which case your graph belongs to. Okay? And we're going to add some noise to this problem to make it a little bit harder. So instead of just having these cycles, you're also going to have some paths of length k. So you can think of this as half the vertices are going to be just set aside for the noise, and remaining half are going to form cycles. And the same thing is true for the other case. You still have these cycles of length k, and the remaining half vertices form the noise, the paths. Okay? And this is, we proved the lower bound for this, and it translated into random order streams. Let's see how that works. So just when you look at it, if you just add these numbers, they're not really important. You're going to get a gap of n over 4k in the number of connected components between these 2 cases of graphs. Right? So if your epsilon was in this range, then you will be able to identify and distinguish between these 2 cases. Right? So if you prove that you can't distinguish this, then you prove that this algorithm doesn't exist too. All right? So next, I want to talk about some history about NGC. So it was introduced by Verbin and Yu in 2011 to prove single pass streaming low bounds in the adversarial setting. Right? And after that, a lot of results, it's not just these two, not just Huang and Peng, which I mentioned earlier, but Kapralov, Kanna, and Susan, and a lot of other works also use NGC or just gap cycle counting problems to prove streaming low bounds. And this was also extended to multi-pass low bounds by Asadi, Cole, Saxena, and Yu, and Asadi N in 21. Okay. So the main thing is NGC is very versatile because you get low bounds for a lot of other problems. There are a lot of reductions and so on. Okay. But one thing is all of these works actually only look at NGC in an adversarial setting. What we're going to do is look at it in a random order stream and see what happens there. Okay. Fine. So yeah, in a random order stream, right, that's why we're going to look at. Let's see what happens. You have this graph. You should think of this as an instance of NGC. It doesn't look like it, I know. So let's keep going. You have Alice and Bob. And this graph is partitioned into two. And this partition is going to be random for us. Okay. And one part is going to be given to Alice, and the other is going to be given to Bob. And then Alice should send a message of some length to Bob. And Bob has to figure out what instance this graph belongs to. What are the cycle lengths, basically. So basically, we're transferring from the streaming model to this model now. Right? So we'll see how low bounds for this model also translate to streaming in a little bit. So is the question clear? You have a graph which is an instance of NGC. Just split the edges randomly into half. Give one to Alice, one to Bob. Okay. So let's keep going. Yes. So why would a lower bound for this problem that we're looking at also translate to streaming? What we can do is Alice is going to try and run this algorithm, any algorithm which is a streaming algorithm, this way. So Alice is going to pick a random permutation of the edges which are given to her, right? And then she's going to run this algorithm on her edge set and send this memory state to Bob. And Bob is going to do the same thing, pick some random permutation, run this algorithm, and output the answer. So why is this good for us? Because what we're trying to do here is emulate a random stream, and that's why we wanted a random partition. Right? So once you have a random partition, you can pick this permutation and just have a random order of the edges. Right? So this way, a lower bound in the communication setting is going to translate to a lower bound in the space used for this streaming algorithm also. Yes?
Yeah, sorry. When you say memory, like send memory, is this is not the state of the memory at the end of running the algorithm or anything? It's
No.
Every.
It's not every, it's just once, basically, because it's just one time that the algorithm has access to the edges. In the middle, Alice will run everything on only this set, and then she'll send the state. And then Bob will run it on his set.
So she sends the state after
Yeah.
she's processed
Yeah,
all
exactly.
of her edges?
Yeah.
Okay.
Some other question is there? Okay. Any other questions? All right, okay. So after this, I'm going to focus just on NGC in this communication setting, right? And what we're going to do is set the cycle lengths, k, to be theta of log n. And this is why this epsilon was going to be 1 over log n for us, because epsilon was order of 1 over k. Okay. And this is right. Like, I'm not talking about any other range of cycles. This is exactly right. Right? Okay. And we want to prove a lower bound of omega of n for NGC. And this will translate to omega of 2 raised to omega of 1 over epsilon for random order streams. All right. Okay. So I'm going to talk next about our techniques. I'm going to focus on two main things. Since this NGC is a communication problem, first I'll talk about this gadget construction for our hard instances for NGC. And then I'll see about reduction of these hard instances to this XOR of index problem. Okay. So just, we can, the rest of this is going to, next part is going to be focused on this gadget construction. Any questions till now? Okay. So this is going to be a bit of a detour, but let's do it because we need this for all the gadgets. And first I'm going to talk about encoding one single bit using groups of 4 vertices. So you have vertex group L, which is on the left, vertex group right. If this bit I want to encode is 0, I'm just going to add edges between the corresponding vertices on the other group. Right? So U1 and V1 are going to be connected if this bit is 0. U2 and V2 are going to be connected if this bit is 0 again. And if this bit is 1, you're going to be switched. Okay. So the edge connections between these sets of 4 vertices is going to encode one single bit for us. And it will be clear why we're doing this in a little bit. Okay. And the next step is to encode a complete string using this same thing, where if the string is of length n over k, we're going to encode it with groups of sets, vertices numbering 4n over k, right, where you're going to have n over k different sets of size 4. So for example, if this string I want to encode is 0, 1, 0, right, the first set is going to have straight edge connections, the next one you're going to be crossed out, and the next one is again going to be straight. Right? So I just want to do this for every bit in my string. Okay? Right. So this part is important for us. This is how we're going to extend it to the actual hard instance too. Okay. So after this, if there are no questions, let's keep going. Yes. Now I want to talk about something, permuting a string, where in addition to a string, you're also given a permutation row. Okay. And I don't have time to talk about what this gadget for row is. Let's just say we have some gadget for row. You can think of it as a black box. And this string that we encoded with this graph gadget is going to go sit in between gadgets for row. Okay. I'm only going to talk about it in the context of what this gadget gives us and what is important, and not get into the details. All right. So this construct with one string and one permutation is going to be called a block for us. And we'll see why this block is going to be useful now. Okay. So this block is also going to have these sets of vertices on the left and this set on the right. And what I want to happen here is the connections, path connections between these groups should encode some other string. And what is this specific string? It's going to be that I have this x already and I have a permutation row of, which is just permuting the positions of x. And I'm going to define a new string y, where in the first position I'm going to have row of 1, in the second position I'm going to have row of 2, and so on. Right? So you're just rearranging the values in x according to row. That's it. And what I want out of this gadget for this permutation is that the the path connections between the left and right groups of vertices is going to encode y. So let's go a little bit slowly here. If this first bit of y, which is the permuted string, was 0, what is going to happen is this first vertex in the first group is going to be connected directly to its counterpart on the right. And the second one is also going to be connected directly to its counterpart on the right. And if this bit was 1, they're going to be crossed out somewhere. Okay. I have not told you how this is happening. I have not told you what goes on inside this row. But let's just say that you can construct this, and this is what we want out of a block, and this exists. Okay. So any questions? Yes?
Is there some reason why the gadget for row is more complicated than just routing the 2 wires for y1 to the
You can do it, yeah. It's more, that just works, but this one should be some inverse. I just didn't want, that's the wrong thing to focus on, basically. That's why I've ignored it, yeah. All right, okay. So the next step is going to be that I'm going to just put multiple things which are these blocks together, okay. And this is also going to have some group here and some group here, which is then going to encode another string. And for this, I just have, whatever, theta of k many different strings, theta of k many permutations, just theta of k many different blocks, right? And you're just concatenating all of them. And after this, what do these different sets encode? It's going to encode the XOR of the different y's I get from every block. Okay. And this is also not hard to see. It's just that, if you have some edge connection here, if it's crossed out, the total number of crossings is just going to be the number of ones. Okay, and that's why that way, if this string z, which is going to be the XOR, if this is 0, then you're going to have even number of crossings, and you're going to be connected to the same counterpart. If this string is 1, you're going to have odd number of crossings. You're going to be switched out. Okay. So right now, all we've done is just take all these blocks and put them together, and then encode this XOR of some different number of permuted strings. Why are we doing all this? Our goal was to create an instance of NGC. Okay. Let's come back to NGC now and see how we're getting these cycles out of this construction. Okay. So if this bit Z1 was 0, right? So what I'm going to make sure is this length, I'm going to enforce it to be k minus 1, and I'm just going to add edges between the corresponding vertices. So this will give me 2 different cycles, which are of length k each. And if this bit was 1, I'm going to have just one cycle of length 2k, because this will be of length k, you go back, length k minus 1 again, and you go back. So it's going to have just one cycle of length 2k. So now, this way, this is how we're getting our cycles, and the difference in cycles comes from the bits. Right? So finally, we want our exact NGC instance, and what we're going to do is just set the remaining half of these bits to be noise. Right? Basically, don't add any edges. And when you do add the edges, that's going to create the cycles for you. As we said, length k if it's 0, 2k otherwise. Okay. And now, let's look at what these strings have to be. If these were just completely random strings, you're going to get a mix of k cycles and 2k cycles, because they can be 0 or 1. You don't have any control over them. So you're just going to force all of these strings to actually be, completely 1 if you want the cycles of length 2k, and fully 0 if you want cycles of length k. And these strings you don't get. Basically, these bits, the remaining half, you don't care, because that's just nice. That can be anything. Okay. Any questions about the hard instance? Yes. So this is how we got the instance. We had some string x, and then we had one permutation for each string. We permuted it with this thing called a block, and then this gray area was just made of multiple different blocks. And then we added these edges for the first half. This was nice, and this part made the cycles for us. Any questions about this? Yes?
What's the purpose of the permutation?
Basically, what I want, we'll see, what I want is for this, maybe I'll answer it in a little bit. You're asking why I even need to permute the string, isn't that it? Yeah. Okay. So now I want to analyze this hard instance and hopefully convince you that this actually looks like XOR of index. But I'm not going to prove it or anything, just maybe give some intuition about this. Okay, fine. So let's just focus on the first half of these groups. All right. So what did we say? We said these all of these n over 2k bits have the same value, right? That's what we forced to happen because we wanted cycles of the same length. Algorithmically, what is this question? You just want to find one specific bit, and if you do that, you're done. You're going to solve this problem. Right? So, yeah, what happened to this? Yeah, okay, this is where I was. Yeah. Now, informally, you can just think of it as, if you want to find one specific bit among all these n over 2k bits with, let's say, constant success probability, if you can find just one bit among these many bits with very low advantage, right, then you're done, basically. Because of the union bound, you're going to find one of these bits. There is definitely a way to translate this through a lower bound, which is a hybrid argument, okay, but we're not going to get into it. You can just assume that if I have a lower bound for finding just one specific bit where this index, let's say it's 1, okay, just this bit z1 with advantage k over 2n, then I can actually have a lower bound for this instance too. Okay. So after this, I'm only going to focus on proving a lower bound for this one instance, and hopefully there you'll see why we need the permutations. All right. Yes. Now remember that what happened in the NGC instance was we had a random partition of the edges. Half of it went to Alice, half of it went to Bob. What is going to happen to any one path in this graph? You have no control over this. Some edges may go to Alice, some edges may go to Bob. Right? And if these permutations were to not exist, right, then Alice and Bob are just going to have, it's like just some bits given directly to them, right? And they can just focus on finding this one bit easily. Basically, Z1 is just going to be a XOR of X1, X2 at the first positions of all these strings, which is not very hard to find. Okay. With these permutations, it'll help us. Let's see how. So this was one block for us. Okay. As we said, the information in this block is going to be split between Alice and Bob. What I want to happen ideally is this entire red part in this block, I want it to go to Alice, and all of these green parts, I want it to go to Bob. But that does not happen. You can't make sure that happens. But what I will be able to get is most of this block goes to Alice, and most of this block goes to Bob, and the same thing is true for this one. So I'm going to call this to be my desired partition, right? And you can prove that a lot of these things will exist. We're not doing that, right? And once you have a desired partition, you can see that Alice has some string, Bob has some information about this permutation, and they have to find this one specific bit, basically Z1, which is going to be some bit, some position that Bob has information about and Alice does not. So maybe this was a little bit too rushed. Let's go with this a bit more slowly and why we're getting XOR of index. Okay. So Alice has information about X, Bob has rho. Let's see. So what is going to happen to the actual graph instance? Some of these blocks are definitely going to be bad because they're not going to obey these partitions. We're just going to fix them and not care about them at all. And we'll still have some of these good blocks, and this is enough to give the hardness that we're looking for. Okay. And here, as we said, Alice is going to have some of these strings, and Bob is going to have some of these permutations. And this bit Z1 that you're interested in is just going to be take xi or x1, and then take this row I of 1, basically what 1 goes to in this permutation, and then just take XOR of all of these bits. So here, if the permutation does not exist, Alice will just know what it is. Okay. So is everything okay? All right. And right now here, what do we want the lower bound for? We have Alice and we have Bob. We're sending a message of length s, right, as we said in this previous communication complexity setting. And we want to prove a lower bound for this length s. Right? And this s, you can actually prove that it's going to be omega of n against this very low advantage k over n. Right? And there are tools to do this. One of them is Fourier analysis. You can use KKL inequality, which was shown by Khan, Kalai, and Lineal in 1988. And then it was adapted for this by DeWolf. And using many of these tools, you can actually prove that this lower bound is omega of n. So once you have this, you're going to translate it all the way back to a lower bound for NGC in random order streams. Any questions about anything here? Okay, so I've not talked about a lot of things in specifics, but overall, this is the intuition for what's happening. Okay, and that's it. I just want to conclude now. So we proved the lower bound of 2 raised to omega of 1 over epsilon for estimating the number of connected components up to some epsilon and additive factor, right? And we showed that this exponential dependence on this epsilon in random order streams, you can't actually avoid it, it's inherent. And there are definitely some open questions here. All of these algorithms in these random order streams, they're actually factorial algorithms, factorial dependence on epsilon. You only have 1 by epsilon raised to order of 1 by epsilon. And we don't have any tight lower bounds for this. And we don't know about extend integrate to other values of epsilon either, because we just proved it for epsilon to be theta of log n, 1 over log n. And finally, when we proved this cycles thing, the length of the cycles, we fixed it to be log n. Just a thought experiment, if this length was anything lesser than log n, it's not going to be hard to figure out, because at least one of Alice or Bob is just going to get 1 complete cycle. Right? So that way, they can just solve it with no communication or constant communication. So this log n that we assumed was actually necessary. So if you can reduce the length just by a little bit to log n over log n, can you actually still solve this? And for that, you're going to need, it's not this Alice and Bob are not sufficient, you're going to need a different model. And that's all I have. Thank you.
In the algorithm, is it easy to point to like which particular places are really taking advantage of the fact, or really rely on it being a random order distributing?
You mean in the algorithm point of view and not the lower bound?
No, like
right?
from the lower bound that you presented, which particular parts are crucial for the randomness?
Yes. So one thing is we started out with the random partition of the edges, right? I think that just solves this random order stream part for you. The rest of that is just going to be analyzing what happens to your instances under this random partition, which we can do, right? So this random partition is not, it's not new. It's called robust communication complexity, which has been introduced before already, and that's what we're using.
Okay, let's thank
Oh, thank you.